Back. We're going to review, well, quite a bit of our atomic theory so far with today's video. Some vocabulary terms as well as understanding isotopes, and then I hope we're finally going to get to something called average atomic mass. So maybe you could take a minute by pausing the video and put the letter P, N, or E, or a combination of those letters beside each of these statements, determining whether or not that is describing a proton, neutron, electron, or maybe two or all three of the particles. So pause the video, do your best. When you're done, press play again, and we'll see how y'all did. Okay? Go for it. All right, welcome back. Number one, most of the mass of an atom. That should be pretty easy. Remember, electrons are really, really tiny, almost 1/2000th the size of a proton. Protons and neutrons have the same mass, so hopefully you put P and N in the blank for number one. Number two, which has a positive one charge, that's a gimme. Hopefully you put P there for proton. Next, how about the mass of one AMU? We learned what an AMU was last time, didn't we? So one atomic mass unit would be a proton or a neutron. Don't they weigh about as much of a hydrogen atom, which has an atomic mass of pretty doggone close to 1 AMU. Okay, which particle or particles make up the nucleus? That's right. Remember, Rutherford discovered the nucleus, protons and neutrons, and electrons are outside that, aren't they? Which particle or particles determines the radius of an atom? No, not protons or neutrons. Remember, the nucleus is really, really tiny. So the radius of an atom, it's made up by the electrons. Now, the electrons are really tiny, but they take up a lot of space, a huge amount of space, don't they? Okay, if an atom were 6 miles in diameter, or radius, I really don't care how you think of it, what do you think would be the size of a softball compared to that atom? Yeah, probably the nucleus, wouldn't it? The nucleus is really tiny relative to the size of the entire atom, and the nucleus is made out of protons and neutrons. Electrons might be the size of maybe fleas compared to that softball, buzzing around that softball 6 miles away from each other. Okay, we just talked about number 7 not too long ago. It's about 1/2000th of an atomic mass unit, and that would be the electron. Number 8, which of those have no charge? That's right, that would be the neutron. Number 9, found outside the nucleus. Yeah, that's the electron. And then finally a charge of -1. That's right, that would be the electron also. All right, now the next chart is a review of isotopes again. You don't need to copy this on a separate sheet of paper. You can probably fit this easily on your guided notes, but if I asked you to turn it in, that's probably how you would do it. So for this, I need to give some information to you. So let's say we have an atom of helium, and I tell you its mass number is 5. For silicon, I give you a mass number of 29. For beryllium, I want to tell you that it has 4 protons and 5 neutrons. For hydrogen, I want to say its mass number is 2. For radon, let's go ahead and let's tell you that it has 86 protons, although you could look that up pretty easily. And let's give it, this isotope, 136 neutrons. For argon, let's give it a mass of 41. And let's give it 18 electrons. Fluorine, a mass of 19. And that's all I want to give to you. For fluorine, for lead, let's tell you that it has, this isotope has 126 neutrons and 82 electrons. So what I'd like you to do is pause the video and fill in everything that's missing. If you can do this, I think you understand how to find protons, neutrons, electrons in any isotope of an atom that I give to you. I think you can do it. So pause the video, give it a whirl, and come back. See you soon. All right, welcome back. Let's change the color here of our key. Let's put our answers in green now. Down below. So helium, if you find the element helium on your periodic table, kiddos, I hope you used your periodic table for this. you will see that it has an atomic number of 2 written above, and that's really the one that we want there. So we know that the atomic number is the number of protons, so you put a 2 here, and that's the number of neutrons, or electrons also. Its average atomic mass is 4.0026, but that doesn't help us find the number of neutrons in this case. Remember, protons plus neutrons equal the mass number. So this isotope would have 3 neutrons, wouldn't it? Okay, silicon. Its mass is 29, so if you looked up silicon on your periodic table, silicon, its atomic number is 14. So we know it has 14 protons and 14 electrons. And let's see, 29 equals 14 plus 15. Good, that isotope of silicon has 15 neutrons. Okay, beryllium, looks like it has 4 protons and 5 neutrons, so it has a mass number of 9. And protons and electrons equal each other for neutral atoms, so we're going to put 4 for the number of electrons. Hydrogen, its mass number is 2, and if you look on your periodic table and find the element hydrogen, it has the atomic number 1, so it has 1 proton and 1 electron. The mass number is protons plus neutrons, so we must have 1 neutron there. Okay, radon. Let's see. Number of protons is 86. Number of neutrons is 136. Remember, protons and neutrons give us the mass number, so we have to find the sum of 86 and 136, and hopefully you all got 222. And for the number of electrons, it will equal the number of protons, so you put down 86. Okay, argon, let's see, its mass is 41. It has 18 electrons. That means it has 18 protons. And so the number of neutrons would be, let's see, would that be 23 plus 18 is 41? I think so. Fluorine, I gave you its mass number of 19. But if you looked up fluorine on your periodic table, which I hope you did, its atomic number is 9. So it has 9 protons and electrons. And it looks like the number of neutrons would be 10. And finally, the last one here, lead, let's see, it has 82 electrons, so let's go ahead and put 82 protons down. And so the mass number will be the sum of 82 and 126. That gives us 208. All right, how did you do on that? Good, I hope. All right, let's, for the final part of our discussion today, talk about something called average atomic mass. I'm not sure we'll have time on this video to do calculations related to average atomic mass, but we'll get to that soon. So, question that you should all be able to answer now, I hope. Do atoms of the same element all have the same mass? No, they don't, do they? We have different isotopes of different elements, don't we? So if they don't all have the same mass, we need to find something called an average mass for all of the elements. Now, some students would think that you would just add the mass of their isotopes together, divide that by the number of isotopes, and that would give you the average atomic mass of an element. But that's not how we do that, because isotopes are not always present in the same percentages. So let me give you a little analogy to help us with this. Let's pretend that unwittingly 30 students walked into our room and we weighed them. They didn't know that we were doing it, but there's a little digital display above their heads. As soon as they walked in, we were able to tell their weight. Turns out that when the 30 students walked in, 20 weighed 100 pounds and 10 weighed 200 pounds. So, what's the average weight of a student that walked in the room? Well, some of you might say, oh, that's easy, Mr. Hummer. I can do averages. Some of them weighed 100. Some of them weighed 200. 100 plus 200 is 300. Divide that by 2, because that's how you find average, Hummer. And you get 150 pounds per kid. And you would be wrong. That's not how we do it. Didn't 20 of them weigh 100 pounds? And only 10 of them weigh 200 pounds? So won't the average kiddos be closer to 100 than it is to 200? It won't be right between the two. More of them weigh 100 pounds then weigh 200 pounds. So how would we do that problem? Well, let's see. To find an average, don't we have to find the weight of everybody in the room? So 20 of them weighed 100 pounds. That means 2,000 pounds so far. 10 of them weighed 200 pounds. That's another 2,000. So didn't all those kids that walked into the room end up weighing 4,000 pounds? Then don't we divide that by the number of students? Yeah, so we have 4,000 divided by the total number of students, which gives us a weight of about 133 pounds for the average student. Now, did any of those students end up weighing 133 pounds? No, they either weighed 100 pounds or 200 pounds. None of them weighed the average. Why is the average closer to 100 than it is to 200? Yeah, because more of them weighed 100 pounds than weighed 200 pounds. The same is true for atoms of the same element. We need to do a similar calculation. So let's take a real example. Let's see if maybe we can find the average atomic mass of a boron atom. Turns out that boron atoms come in two different types of isotopes, boron 10 and boron 11. Obviously, one has 5 protons and 5 neutrons. The other has 6 neutrons, still 5 protons, kiddos. They exist in nature as 20% boron 10 and 80% boron 11. And their experimentally determined masses are either 10.0 atomic mass units or 11.0 atomic mass units. From this data, we should be able to calculate the average mass and then check it on the periodic table, because the periodic table lists the average atomic mass. So let's see, 20% weigh 10 atomic mass units, and 80% weigh 11 atomic mass units. Won't the average be closer to 11 than it is to 10? Some of you are saying, well, how do you know that, Mr. Hummer? Well, because 80% of them weigh 11. Only 20% weigh 10. So won't the average be closer to 11 than it is to 10? Yeah, it will be. So how are we going to do this? Well, I would suggest doing this. Let's find 20% of 10. Okay, that would give us 20% of the average mass. So to do that, don't we take 0.20 times 10? And that equals 2.0. So 20% of the average atomic mass is 2. And then let's take 80% of 11, so 0.8 times 11, and that equals, of course, 8.8. So 80% of the average atomic mass is 8.8. Well, let's add these together. That way we'll get 20% of the average mass plus 80% of the average mass will give us 100% of the average mass. So 2.0 plus 8.8 is 10.8 atomic mass units. That would be the average atomic mass. Do any boron atoms weigh 10.8? No, they don't. They either weigh 10 or 11. So none of them weigh 10.8, but that's the average. Isn't it closer to 11 than it is to 10 like we thought at the beginning? Yeah. And then finally, we find the element boron on the periodic table. Its atomic number is 5. But down below, we're going to see an integer. And it gives us the average atomic mass, which says 10.81. Hey, we did pretty good. Didn't we get that average atomic mass with the data I provided to you? We sure did. All right. Good job, kiddos. We'll talk to you soon. Bye-bye.